All right, the lesson we're working on today is going to be over exponential functions, which are the inverse of logarithmic functions. So we're going to work a little on exponential, and then we're going to switch over to logarithmic and be able to switch back and forth between the two different forms. We actually need one form in order to be able to solve the other. So first things first, the exponential function is always going to be some function notation, f of x equals some base, which this is some number, to the x exponent. So what makes an exponential function is the fact that there's a variable in the exponent. So there could be multiple different variations on it, and all of those would be different transformations, but this would be considered like your parent function for an exponential. Down here, please note that a cannot be 1 because 1 raised to any power is still 1, which is going to be a constant function. That's just your horizontal line. It's not an exponential function. All right. Next thing down here for the example, we're just plugging these values into the calculator, so I'm pretty confident you guys would be able to do those. For this one, 2 to the negative 3.1. Here we're plugging in a pi, so it would be 2 to the negative, and then we put a pi here. And then our value here, 0.6 to the value of 3/2. So the solutions for those are some lovely decimal numbers. This one's 0.1166. This one is 0.1133, and this one is 0.4648. So just make sure that you can plug those into the calculator and get these solutions, but most of you guys are pretty calculator savvy. You can do those just fine. All aggressive exponential functions are going to look fairly similar to one another, so we want to sketch these 4 graphs real quick and see if we can come up with like what's making them do what they're doing. So for the first one, we have 2 to the x power, and then we also have 4 to the x power. So the difference is going to be when I have 2 to the x power, if I say 2 to the first power, that's going to be a 2, so I'd plot the point right here, and that's going to be for this one. I'll color code them. So 2 to the x will be here, and then if I do anything to the 0 power, okay, so if I made my x value 0, anything to the 0 power is going to be 1, so it's going to cross the y-axis at 1. When x is 0, y is 1. And then it's just going to extend down this way. It's actually got an asymptote down here at 0, and it'll extend up like that. Okay, and we can fill in a table of values here. If we said 2 to the negative third, we would have 1/8. 2 to the negative 1/2 is 1/4. 2 to the negative 1 is 1/2. Remember, we kind of worked on these negative exponents with that logarithm activity. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. And then 2 to the third is 8. Okay, 2 to the second is 4, so I guess I kind of missed that value a little bit. Coming out this way a little bit more then. Okay, we'll do the same thing with the 4. So 4 to the x power, so now we're using a base of 4, and I'll change my color. Let's do some green now. So if we did 4 to the x, 4 to the negative third would give me 1/64. 4 to the negative second is 1/16. 4 to the negative first is 1/4. 4 to the 0 is 1. 4 to the first is 4. To the second is, 16. And to the third is 64. So you notice we're growing very, very quickly there because of our values, because of our base value. All right, but notice over here, your numbers are extremely small. You're getting very, very close to the x-axis. That is that asymptote rule, okay? So we've got a 1 here, and then at 1, we're at 4. So we're going to grow much, much, much faster. At 2, we're already at 16, so we're up here. So notice when that base is bigger, what's happening is that we're actually going to grow a lot faster. All right, so 2 to the negative x and 4 to the negative x. Let's see, how is that going to change what my function is going to look like? So this guy was in green. The next one's going to be 2 to the negative x. So now if I plug in a negative 3 where the negative x is, a negative times a negative is a positive. So now we have 2 to the positive third, which is 8. We did those up here. So what did that negative end up doing to my graph? Because now all of these values have switched. Okay. At 0, we're still at 1, so my point is still here. But what's happened is that my values have now been reflected over the y-axis. And at 3, we're at 8. Okay, so we're going to come in like that. And that's for this one. And then our last one down here. Concept is the same when the x is negative up here. And if you'll remember your transformations, this would be like your b value being negative. And remember, a negative b value is what reflects it over the y-axis. So that's why it did what it did. So again, this would be 64. I'm going to have 16, 4, 1, 1/4, 1/16, and 1/64. Still crossing here at 1, and then 4, we're here, and we're all the way up here. So again, very, very steep because of that base value, but reflected over the y-axis because the x value or the b that was in our transformation stuff is negative. Okay, we call these guys, the red and the blue, because they're going down as we move from left to right. We call those decay functions, and the ones going up from left to right, we would call those growth functions. Okay, compare and contrast the 4 functions above. We've kind of just done that a little bit. Notice that when that exponent was negative, it's reflected it over the x-axis. They all had the same y-intercept because anything to the 0 power is 1. So the way we would have to move it up and down is by adding that k to the back side of it, just like we did with our other functions. So the transformation is still going to be the same. All right, using the properties of exponents, c and d can be written with positive exponents. So if I have a negative exponent, like 2 to the negative x, and I want to make it a positive exponent, the way that we would do that is by reciprocating the base. And we talked a little bit about that with the logarithm activity. So I would reciprocate the base here, and that creates a positive exponent here. So 2 to the negative x is the same thing as 1/2 to the positive x. Same thing for the 4 to the negative x. And notice for each one of those, when we were plugging those values in, I never got a negative solution. Okay, so a negative exponent is not necessarily making a negative solution. That's not going to work. What a negative exponent does is it reciprocates the base. All right, from example 2, there's basic characteristics of the exponential functions. So if we have a to the x, this would be the growth function. That's the one that's going like this. Versus this one, a to the negative x, that was your decay function. It was reflected over the y-axis, so it's coming down like that. Okay, they're all going to be continuous. In other words, there's no holes or breaks or anything like that. I can draw the entire function without picking my pencil up. For both, we have a horizontal asymptote at the x-axis. You guys can kind of go through the rest of that information. That's just basic function information, just like we did with our other parent functions. Okay, because exponential functions are always increasing or decreasing, they pass the horizontal line test, which tells us the functions are one-to-one. Therefore, we can use the one-to-one property to solve simple exponential equations. Excuse me. Passing the horizontal line test, remember that tells me that if it passes the horizontal line test, then that tells me that the inverse of whatever it is that's being graphed on there is a function. The inverse is a function. That's what that is telling me when it passes the horizontal line test. Okay, why does that come in handy? Well, basically this is saying if you've got 2 bases that are equal to one another, a and a, then that means their exponents also have to be equal to another. So that means x would have to equal y. So if we come over here, we're going to try to make the bases the same, because if we can make the bases the same, then the exponents would be equal to one another. We can just set the exponents equal to one another and not have to worry about the bases themselves. So we always look at the smaller base. So this is a base of 3. I want to try to make the 9 into a 3. So what's the relationship there? Well, I know 3 squared is the same thing as 9. So all I'm going to do is change the 9 into a 3 squared. I'm going to leave the other side alone, so we have 3 to the x plus 1. Okay. Now that the bases are the same and we have a 3 equal to a 3, the 3's basically cancel themselves out. You just set the exponents equal to each other. So 2 equals x plus 1, which means x has to equal 1. All right, and you can check that. If you put a 1 back up here, 1 plus 1 is 2, and we know that 3 squared is 9. Try again over here with this one. Going back to that negative exponent thing, I don't want a fraction if I can help it for the base. So instead of it being 1/2 to the positive x, let's make it 2 to the negative x. Make it a little easier to work with. So we have 2 to the negative x equals 8. Now, can I turn that 8 into a base of 2 also? In other words, I made both of these bases, or I'm going to make both of these bases 2. So 2 to the negative x is equal to 2 to the third, because 8 is 2 to the third. So then our x's or our bases cancel each other out, and we say that negative x equals 3, which means x has to equal negative 3. Okay, talking about transformations, again, these transform in the exact same way as our other parent functions did. So if we're talking about this parent function 3 to the x, if I do a plus 1 up here in the exponent, that's going to be grouped with the x. So then that 1 is going to be, remember, an a, a b, an h, or a k. Well, it's being added to the x, so that's going to be an h. Okay, and if it's added to the x, then the transformation here would be we're going to be shifted to the left. Remember, it goes opposite of the sign, so it shifts left 1. Okay, so you have these values down here, the points down here, like this one here and this one here. So we're going to take those points and we're going to move them all to the left by 1. So that one goes there and that one goes there. And then we follow along like this. And there's the transformation of that graph. Okay, try again with b. So on this one, I have 3 to the x minus 2. Minus 2. Is that an a, a b, an h, or a k? Well, it's tacked on to the end, so that's our k. What does that do? That's going to shift us down by 2. So now we're going to take these same points that I just used a minute ago, only now we're going to shift them down 2. 1, 2, and 1, 2. That's also going to shift my horizontal asymptote. Remember, my horizontal asymptote was going right across here. And anytime you shift up or down, that horizontal asymptote is going to move with it. So if I shifted it down 2, my horizontal asymptote is now down here. All right, so now we follow along the new horizontal asymptote that's been moved. Let me connect the dots up this direction. Okay. Horizontal asymptote no longer there. All right, let's take a look at C. I think this was probably a typo. I'm not sure why that was there. I think I'm trying to, on this one, do a negative 3 to the x. Negative 3 to the x. So that negative out in front, is that an a, a b, an h, or a k? And that one's going to be our a. And remember, if a is negative, that's going to be a reflection over the x-axis. Okay, so again, we're taking those 2 points, and if I'm reflecting over the x-axis, my horizontal asymptote is going to stay right here. This point is just going to come down here, and this point is going to come down here. So we still follow along the same way. I'm just going to go down like that instead. And our last one, we'd already talked about this one a little bit. Because it's grouped up there with the x, it has to be either a b or an h. Because it's being multiplied to the x, that's going to be our b value. So this little guy right here, you can't even see the function anymore. That little negative right there is our b. I don't know why I put quotations, because I didn't do it with any of the other ones. And because our b is negative, this is going to reflect us over the y-axis, which is what we just did a little bit earlier. So this point reflected over the y-axis is not going to go anywhere. It's already on the y-axis. But this guy is going to come over here. And now we're going to decay. We're going to go down as we move from left to right. All right. Notice all the above transformations kept the x-axis as the horizontal asymptote, except when you're doing a vertical shift where you're moving it down to y equals -2. Okay, also note how it affects the y-intercept for each. So the y-intercept was the same for when we did the reflection across the y-axis, but it ended up changing it to negative over the x-axis. Okay. Base E, because it looks like a letter, a lot of people want to try to make it a variable. E is not a variable. It's actually a symbol, so that's how I want you guys to recognize it. So we look at pi, and because pi doesn't look like one of our letters in our alphabet, we know that's a symbol and it represents 3.14. Okay, another irrational function is the natural base, which is base E. So again, this one looks like one of the letters in our alphabet, so we think of it as a variable, but it's not. E will always represent 2.72-ish. Always, always, forever and ever. All right, so anytime you see E, think number 2.72. It is not a variable. So you can create an exponential function with this natural base. So it would be f of x equals e to the x. Okay, again, e is the base. E is about 2.72, so we're saying 2.72 raised to the x value. And again, we're plugging the values in, each of these x values with the calculator. So we're raising e to the negative second, negative first. Again, I'll give you those solutions. My calculator is not working, so I can't open the calculator up and actually show you how to type those in. But the E button is on the LN button on the far left side of the calculator, and you'll have to do second to get to the E. So it's second and then the LN button. All right, your solutions when we do x is negative 2, 0.1353. When it's negative 1 is 0.3679. When we do 0.25, we get 1.284. And for D, when we do negative 0.3, we'll get 0.7408. Again, make sure that you can type those into the calculator and you do get those solutions. So you're going to do 2, and then your E is actually down here on the natural log, because E and natural log are actually inverses of one another, so they share a button. So you'll press second and the natural log button to get your E, and then we're raising that to the 0.24x. And then we're just going to go to the table and grab our values. Now I'd like for you guys to set the table up so that you can put your own x values in. So if you'll go to second and table set, you want the independent variable to be on ask. If you'll do that, now when you go back to your table, there's no x values. Now you get to choose what x values you want to put into the table. In this case, we're going to put in those values right there. So negative 3 to 3. But if I was skipping around a lot, or I wanted like a negative 5 and then a 1 and then a 7, if you want to just plug in random values, you could do that using the table setup the way that it is. Oop. Let's try that again. How about negative 3, negative 2, negative 1, 0, 1, 2, and 3. Okay, so now we just need to take these values here and transfer them over to the table here. So we have 0.974, 1.238, 1.573, 2.543, 3.232, and squeezing that last one in, 4.109. Then we would just want to take those values and plot those points. So I'm going to plot a negative 3 and approximately a positive 1. So we'd have negative 3 and a positive 1, pretty close. Negative 2, just a little over 1. Negative 1 would be about 1.5. 0 would be at 2. 1 would be at 2.5. 2 would be at a little over 3. And then 3 would be at 4. And then we'll connect those points. Because this is an exponential equation, we know that there's going to be a horizontal asymptote. And since there was no shift vertically, the horizontal asymptote would be at your y equals 0. So you should have a horizontal asymptote right here along the x-axis, meaning that this graph is never going to actually cross the x-axis. So try this with the second equation, the g of x function that you have here. Try to plug that into your calculator, come back, and check and make sure that you got that all graphed correctly by hand. Okay, if you're back, hopefully you were able to figure out these values based off of what you got in the calculator. So in the calculator, we should have plugged the function into y equals. And in our table, we had our same x values, plugging those in to get these y values. What I do want you guys to notice, two different things with this particular function. Because the exponent is negative here, the graph is actually going to decrease as you move from left to right, so we call that a decay function. Let's do that in orange so it matches. Versus a function like this, where we're growing or increasing as we move from left to right, would be a growth function. Also notice this function does not touch the x-axis either. As it's decaying, it still has a horizontal asymptote at y equals 0. The only way you wouldn't have a horizontal asymptote at y equals 0 is if we had some kind of vertical shift. That would be by adding some number back here to the back, like a +2. Then my horizontal asymptote would be shifted up 2, and so would all of my coordinate points. But that only happens if you've got that k value tucked onto the back of your function. That should be it as far as graphing with the calculator. So then an application of an exponential function says one of the most familiar examples is continuously compounded interest. What that means is that you're calculating the interest at certain intervals during a particular year or in a year. The formula is derived from the compound interest formula. So this guy right here is going to be your compounding interest. This is where you calculate. So if I want to do it, calculate it at 4 times a year, you put in a 4 here and here. This rate would be your percentage that you're growing by. Okay, but continuously compounded interest, we're going to be calculating it all the time. So it like never stops. That's the idea. So then this guy right here is your continuously compounded interest formula. So anytime you see in a word problem where it's continually compounded, you're going to use, we call this the PERT formula. Okay, A is going to be your final amount, P is the principal, this is what you started with, R is the rate, and you definitely need to put it in decimal form, and then T is going to be the time that you're compounding it. So we have a total of $12,000 invested in an annual interest rate of 9%. Find the balance after 5 years if it is compounded quarterly, then monthly, and continuously. So if it's being compounded quarterly or monthly, if I can count the number of times that it is compounded during the year, I use this formula up here. Okay? If I cannot count the number of times it's being compounded per year, that's because it's continuously compounded, and that's where I'm going to use the PERT formula here. So for A and B, I would need to use this formula, versus on C, when it's compounded continuously, I need to use the PERT formula. But we need to figure out what our variables are in the problem. So if it's a total of $12,000 is invested, this total becomes my P. And it's an annual interest rate of 9%, so we need to put that in as 0.09. We change it to a decimal. And that becomes my R. And then find the balance after 5 years, so that is going to be my T. Now it's a matter of just plugging it into each of the formulas. So if it's compounded quarterly, how many times per year would that be? Well, it's going to tell me my N is 4. Remember I told you guys up here, N is the number of times. So if it's being compounded 4 times, that's your quarterly. Okay? So our formula, A equals P, and then we have 1 plus R over N to the NT. And it's just a matter of plugging everything in. So A equals 12,000. And then 1 plus our R is 0.09. Our n is 4, and yes, you use that same n again up here because this is to the nt, so 4 times, and our t was 5. Okay, so when we go through and calculate all of that, I don't have that value sitting right here in front of me. I have to take a look. We should have $18,000, 18,726.11, so an 11 cents, right, after 5 years. Monthly, if we're compounding it monthly, so that would be n of 12, because you're going to do it one time a month, and there's obviously 12 months. So the difference for this one, when you're plugging into the formula, exact same formula, only down here, instead of it being 4, it would be 12. And then up here, same thing. All right, so now I'm getting that calculated interest 12 times a year instead of just 4. My total, $18,788.17. Did we really get a whole lot more there? You would think if it's being compounded, 8 times more during the year, I'd get a whole lot more money, but not really too much more. But goodness, if we're compounding it continuously, I know I'm going to get a lot more money, right? All right, compounded continuously, that's where we have to use our PERT formula. So P e to the RT. My R and my T are still 0.09 and 5. And remember, E is not a variable. Oh, and my P is still the same as well. So it'll be 12,000 e to the 0.09 times 5. And we plug all that into the calculator and we get a grand total of $18,819.75. All right, so we compounded it continuously for a total of 5 years. What's our difference? Like, didn't get a whole lot more money into that. So a lot of people will think that compounded continuously, you're going to gain a lot more money that way. It really doesn't happen. Okay, but good application of just exponential functions in general, and then also your natural exponential function.